everyone. Good morning. Thanks for getting in so early. It's good to see everyone. I hope everyone had a good evening last night and is looking forward to your half day today. But before you get to go enjoy your half day, let's talk about extended source photometry. Okay, so like yesterday, the first thing we're going to do is talk about our learning objectives, but also like yesterday, the zeroing thing we're going to do is exit out of this meeting recording screen so you can actually see my slides. So today we're again going to think a little bit about this abbreviated Bloom's taxonomy and think about these different levels of learning. Starting from remembering and understanding, we'd like to be able to explain how extended source photometry is different from point source photometry, which you thought a lot about earlier this week. Then going up, identify potential challenges of extended source photometry and possible solutions. So more than just identifying what's the difference between a point source and an extended source, what are the challenges that come into doing extended source photometry and how to think about new ways to really surmount these challenges. And then leading on from that, how are methods for extended source photometry developed? So this is more about taking this knowledge base that you know and trying to expand it into more modern techniques or trying to think more open-endedly about how to tackle problems in extended source photometry. And then finally, as yesterday, we'll go on to the create step with the problem set. One thing that I want to say is that we cannot hope to cover even a fraction of the wide world of extended source photometry and all of the techniques that people use in just an hour. And that's really not the goal of the lecture. The goal here is to develop a framework to understand how and why methods are made. So you don't just have a dictionary of, these are all of the ways that people do extended source photometry, but hopefully you'll be able to think about a framework of this is why we do extended source photometry, and this is how I can tackle my specific problem as it relates to this topic. Okay, so first, point source versus extended photometry. Here, I'm showing a surface brightness profile of a galaxy. This is radius, really it's radius to the 1/4 power for scaling reasons, but you can just think of it as radius. Here, I'm showing surface brightness. The gray curve here is the PSF. So this is how the light would spread if the galaxy were just a point source. And then the red curve here is the actual light of the galaxy. So extended sources are really kind of what they say on the tin. They're spatially resolved and their profile extends beyond the point source function. So it's pretty easy to define what an extended source is versus a point source, at least in theory. If it's broader than the PSF, it's an extended source. If it is the PSF, it's a point source. In reality, though, extended sources come in many flavors. So here I'm showing an image from the LSST First Light Sky Viewer, and I think it's awesome to be able to lecture specifically in this session because this is the first session where we've been able to show, LSST First Light images. So it's not just saying, okay, when LSST comes anymore, when Rubin comes online, but it's really, now we're at the precipice of thinking about the survey start, which is super exciting. But what I want to point out here is that, of course, we have very nearby galaxies. This is obviously an extended source, right? This is not a point source. We can see so much substructure in it. It extends over a very, very large area of the sky. But if you zoom in on this tiny box within a small region of the LSST First Light images, you also see a lot of extended sources. So here, this is obvious in the sense that you can see a disk. You can also see that this is extended compared to these more point source-like objects in the back. So you have extended sources at much smaller scales than these very large nearby galaxies, but you also get into this kind of ambiguous regime. So is this a point source or is this an extended source? So in this regime, you also have to think quantitatively about what is the evidence for it being beyond the point spread function. So there's very obvious cases where this is a giant galaxy, this is not a point source. There's these smaller but still clear cases where you see a disk, you see a lot of structure that extends beyond the point spread function. And then you also have this ambiguous regime where it's not quite clear, at least qualitatively to your eye when you're looking at these images, whether this is an extended source or a point source. So extended sources, lots of different ways that they can be in these images. Okay, so extended source photometry versus point source photometry. You learned about point source photometry on Tuesday. What additional information or complications might arise for extended sources? And let's try just taking hands instead of discussing first. Does anybody have anything that they think would be an additional information or additional complication for extended sources? Yeah.
So I feel like they're not symmetrical, so if you're trying to do the Gaussian thing, then you can't just grab the Gaussian and turn it around. It might look different when you're looking at it.
Yeah. So if you're thinking about trying to measure the light within a certain region, because you now have this spatially extended source, you can't necessarily put down a circular aperture. You might get a very different answer if you put down a circular aperture versus a more elongated one. Yeah, in the back.
Yeah, it's kind of wrong that doing a circular aperture, those objects are quite ambiguous. We can't tell if that's just like one galaxy or like multiple. Or field of view.
Yeah, that's an awesome point. So there's ambiguity about how to deblend objects and how to fragment them into different physical ones. Yeah.
Yeah, so now stacking will present multiple different challenges because diffuse sources like this will bleed into different pixels on our observations. So stacking them and even if our alignments are different and trying to stack them, you're going to get, because they're non-Gaussian profiles, you're going to get, different spikes in flux across different pixels across. Yeah.
Yeah, so if you have different geometric registers, you can also induce kind of biases in how you measure its shape. Yeah.
Talking about for comets, for us, the level of diffuseness can change over time. So if you're stacking different levels of diffuseness, you can smear out any of that sort of interesting information that you would measure otherwise in a single image.
Yeah, that's a great point that I think a lot of other areas of astronomy don't really have to deal with, but time variability in the shape of the diffuse light that you can essentially average over if you go too far. So those are all challenges that you have with extended source photometry. What about more information you can learn with respect to when something is a point source? Does anybody have any thoughts about why it would be nice if sources are extended, not just a problem? Yeah.
So one of the sources that I work on is a huge extended source. It's a giant jet. So one of the things that we're able to see is, precession, variability, proper motion. Those things are easier to, I guess, see in an extended source compared to something that looks like a single DSF. So
Yeah, exactly. So you get more information about the shape, you get more information about the morphology. And that's good in the sense that you get more information, but the more information that you have in the image, the more information that you have in the image, the harder it becomes, or the more information you need to properly account for all of the differences in that morphology. So these are all things that I think we already discussed. So we can measure sizes and shapes that you mentioned. You don't know what the observed profile could be, which makes the blending harder, which you mentioned back in the back. Sources blend together. And then there's ambiguity in what is one source versus more. So I'm gonna take a quick dive into this ambiguity and the ambiguity of blending. But first, let's talk a little bit about image segmentation. So segmentation is the process of identifying locations and boundaries of extended sources or point sources, but we're going to talk about extended sources today. Process of identifying the locations and boundaries of these sources from an image. So in a schematic sense, you can think about an image of some galaxies. Here, these are my galaxies. And if you collapse this down into 1D, you're really doing this in 2 dimensions, but it's easier to kind of visualize in 1 dimension. You might have pixel index on the x-axis, and then this is flux on the y-axis. So say you have a sky background and you have some threshold over which you say, okay, if my pixel is above this threshold, then it's going to be a significant detection. Using this type of algorithm, this class of algorithm, you can identify, oh, here's my object 1 over here. Here's another significant cluster of pixels. This is my object 2 over here. And that allows you to both identify the positions of these objects and also their boundaries. So if I see a galaxy, my boundary is just what I'm saying belongs to the galaxy versus light outside of the galaxy. To give you an idea of what this looks like, so there's different challenges in doing image segmentation, right? So relative to objects that have a sharp edge, galaxies kind of peter out. They have very extended surface brightness profiles, right? So now there's some ambiguity in what we define as the edge of the galaxy. And that means that there's some choices that we make in setting these boundaries for image segmentation. So you could imagine, for example, if you set a very high threshold for image detection, you might only get the cores of galaxies, or you might just be detecting very bright sources in the inner regions. If you set a very low threshold, you might get most of the galaxy, you might get a much larger radius, but you might start to blend different things together. So let's talk a little bit about deblending and fragmentation. Deblending is the process of separating which pixels, or sometimes fractional pixels, belong to what source. So this problem is one that gets harder with survey depth, which I think means that it's more important now than ever to talk about deblending and how we kind of deal with it. So here I'm showing an image from the Legacy Imaging Survey. In this case, it seems like all of the sources are pretty well separated. Like we can pick out, oh, here's a source, here's a source, here's a source, here's a source, here's a source. And there's not that much light above the background noise level that connects these galaxies, right? So if you think about it in our 1D toy model, you can say, okay, you have your one significant cluster of pixels here. This is object 1, and everything else is below the sky background threshold. So it makes it easy to say, this is where I'm going to draw my galaxy boundary, and it's separate from everything else. Separated by sky, nice and clean, and quote unquote easy, which is only easy relative to if we think about something like LSST. So now here again is the LSST first light imaging. This is the same galaxy, but you can see now that a lot more sources pop out. So in particular, if we look at our central source, there's now a lot of smaller background sources behind this. And what this looks like in 1D is essentially you're dropping down the background sky level. So all of these sources that used to just look like noise, that weren't significantly detected, they're now significantly detected. And because they're so close to the central galaxy, you're introducing a new problem, which is deblending, of saying, okay, if I now have this cluster of significant pixels here and this cluster of significant pixels here, and they overlap, there's no sky or noise between them, how do I know what is the same object and what is a different object? You might say, well, I can see that with my human eyes, I can see that looks like a different source and this looks like a different source. But in general, to do this algorithmically, it requires a lot of choices. And yeah.
I'm sorry, this might be a stupid question, but is there a way to confirm whether these objects are spatially correlated with each other or not using spectral analysis?
Yeah, definitely. So one thing that the best kind of way to figure out whether something is a chance alignment or actually related is to get redshifts for them. One of the problems is that, so the legacy imaging data, I know it looks not as deep as LSST, but it is really deep, which means that getting spectra for all of these little faint dots would be super hard, would be very resource intensive. So we'd like to have some way to separate out things, even if we don't know the distances. Yeah.
I have a question about our 1D toy model. When we're looking at the PSFs, we weren't just having some threshold and looking at things, we were involving with like point sources with the PSF having some.
Yeah.
Are we doing something similar
Yeah, so we'll talk a little bit about how we can use the information with the PSF to make our deblending better at the end. But essentially, one of the extra challenges you have with deblending objects for extended source photometry as opposed to PSF is you don't know everything shaped like the PSF. So because you don't know the full surface brightness profile, it makes it harder to deblend because you can't forward model like, okay, I have two PSF-like images here. Now I have maybe a PSF-like source here, and then something that looks like something in the middle. Okay. So, right, just as you asked, because we don't know the light profile of the extended sources, in order to do this deblending, we either have to rely on the pixels themselves. So say we set a threshold for when something should be deblended or not, or set a color threshold or something like that, or start to make assumptions about what the underlying surface brightness profiles of these galaxies are. So here I'm showing work from a more recent deblending technique, which essentially it creates scenes of galaxies where you have data on the left. Every number is a detected peak or significant detected peak. And then the middle is called constrained matrix factorization, where you essentially try to say every galaxy is going to have a single color and it's going to be monotonically decreasing its surface brightness as you go up to larger radii. And you try to construct galaxy-like SEDs, so spectral energy distributions, and galaxy-like morphologies from this assumption. And then the right-hand side here is the residual between the two. So you might expect, for example, if you have a galaxy with a lot of substructure, it might not do a great job of capturing all that clumpy substructure because that violates our monotonically declining surface brightness profile, right? And you can see like this thing that might be related to the galaxy, it might be a background source, it pops up in the residual, you have some significant residual in the bulge. And you can kind of see the imprint of the spiral arms here. So this is just to say that we have techniques to try to overcome this lack of knowledge about what the surface brightness profile looks like compared to point source photometry. But that lack of knowledge means that we have to make assumptions, and those assumptions are usually not perfect. So deblending is one end of the challenge. The other end of the challenge is called fragmentation. So fragmentation is when deblending kind of goes too far and single objects are fragmented into multiple sources. So if we look at this galaxy, for example, here's a GRI composite image. I think this is from Legacy again. But we have this spiral galaxy with a lot of substructure. And then we have a couple different either background galaxies here or things that might be associated with the galaxy but are probably in the background here. And ideally, what we would like to do when we separate out this source is say, okay, all of this substructure should belong to the middle galaxy. These little H2 regions and all these overdensities in the spiral arms, that belongs to the main galaxy. But these little dots and this big dot over here, that should not belong to the galaxy. So that's easy to do kind of when you're just thinking about it in vague terms, but algorithmically it's very challenging. So if you have a kind of overzealous deblender that's trying to do a really good job of separating out things like this, you can also get the case where one object gets broken up into several smaller objects. So here again is a pixel index versus flux. Now let's say we have a clump of significant pixels here. Fragmentation is when in reality all of these pixels are kind of the substructure here, but our segmentation algorithm divides it up into object 1, object 2, object 3. So what that looks like in practice, here's my GRI composite image. This is segmentation that I did that is with very zealous overblending, or sorry, very overzealous deblending. And you can see that this spiral galaxy gets completely shredded, completely fragmented into many different pieces. So it does an okay job of saying, okay, this thing up here, that's not part of the main galaxy. But all of these kind of spiral arm substructure down here, these all get separated out into separate quote unquote galaxies. So this isn't the behavior that we want. But if we go too far in the other direction, we can get under deblended galaxies. So now this is our deblending algorithm is a little bit too scared, and it's saying everything is part of this main galaxy, and I'm just gonna separate out things that are very well separated by sky background. And here, not only does the main galaxy kind of eat its companions in a segmentation sense, but even kind of nearby galaxies that are on top of maybe the more extended diffuse regions of this galaxy get consumed by the main galaxy ID. So there's a play between segmentation or between fragmentation and deblending. So if you over deblend, then your galactic substructures get broken down into smaller pieces and separate objects. If you under deblend, nearby galaxies really get flagged as substructure of these brighter objects. So we want to be in the middle. We don't want to over deblend and we don't want to under deblend, but what are the actual strategies to balance fragmentation and deblending? So I don't think that there's a silver bullet that can answer every science case where we have this great single catalog that can do everything for everybody's science. And in practice, not every catalog needs to serve every science case. And often science-specific catalogs are useful or completely necessary. So for example, nearby and large galaxies will often receive their own photometric catalogs. This can be something like the NASA Sloan Atlas, which is back with SDSF that some of you may have worked with. And this is to prevent these very large nearby galaxies from being fragmented. And in this type of catalog, we say, okay, we don't care about the little dots at redshift 3. We're just going to try to do a good job of containing all of the substructure and all of the kind of diffuse components of these larger nearby galaxies and bring them into one object. Another science-specific use case that I know a couple of people in the room work on are very low surface brightness objects. So these are objects where the central surface brightness is much lower relative to what we call high surface brightness galaxies. And again, in this case, science-specific catalogs can be very useful because you're looking for things that are close to the noise threshold. So these catalogs need to be really cleaned and really vetted. And that's not something that you want to do for your main photometric catalog. If only, let's say, 1% of your sources are true low surface brightness galaxies, you don't want your main photometric catalog to be clogged up with the 99% of other kind of low surface brightness artifacts. And then point source catalogs are also an example of a science-specific catalog in a sense, and that you're just looking at the point sources and you don't care about the extended sources. So really, a strategy to balance deblending and fragmentation is to say, I want my catalog to serve my specific science case, and I would like my catalog to do this science well. Right. And all of these catalogs also have drawbacks for other areas of science. So nearby large galaxies would under deblend small galaxies. Low surface brightness galaxies catalogs also would tend to under deblend small galaxies because they're looking for the diffuse halos of kind of nearby systems. And then point source catalogs would tend to fragment large galaxies. Okay, so now that we've talked about image segmentation and trying to figure out where the objects are, let's talk a little bit about actually measuring photometry from these objects. So multi-band photometry, let's say we have two bands, G and I, and here I'm showing a slice through their PSS, so this is pixel index versus PSF intensity. Let's say the G band slightly better, right? So its PSF is narrower with respect to the I band. And we'd like to measure G minus I color. So G minus I is just going to be the magnitude of the G band minus the magnitude of the I band, which is negative 2.5 times the log of the ratios of their fluxes. But because they have different PSFs, doing forced photometry at fixed aperture is going to make the G band appear artificially brighter. So if you, let's go back to the point source case. And did you guys talk about PSF convolution and multi-band photometry in your point source photometry lecture before? Yes, no, no. Okay, so let's think about just the point source case first then. So if you have pixel index and you have these two PSFs, let's say these are just two measurements of one star. If I took an aperture that is this size here, I would tend to say that the G band is always slightly brighter than the I band. And that's because this aperture captures more of the total PSF of the G band. So I would say, wow, the universe is really blue. G minus I, oh, G is always brighter. But that's not really what I want to physically measure, right? So some solutions are image pretreatment. So this is PSF matching. And what this is doing is convolving all of our images to the worst scene. So let's go back to saying we just have a star. I can say, okay, I don't want to just measure aperture photometry because then I'll measure everything as blue, but I know what the PSF is in G and I know what the PSF is in I. So I can convolve, I can create a matching kernel that takes the PSF in my G band, my better seeing, and convolves it down to the image quality of the I band. And then I can do aperture photometry because they have the same image quality. We'll talk about this more specifically for the extended source case in a second. Another thing you can do is PSF modeling. So one example of this is the Gaussian aperture in PSF or gap photometry. And this is essentially where you're trying to directly model the PSF with some set of basis functions to allow you to measure very accurate colors. So when I say colors, I mean the magnitude difference between your two bands. So I'm trying to model the PSF to get an accurate sense of if I had a different imaginary aperture for every band, what would the accurate color be between these bands of different seeing. The trade-off with methods like this is that you don't really recover the total flux. So in cases where you just care about the color, but you don't care about the total flux, this is great. An example of a case where that might be true is if you're trying to do photometric redshifts. So in photometric redshifting, we're trying to look at the distribution of light from the galaxy as a function of wavelength, and we're trying to fit models that change with redshift, or we're trying to move models across different redshift bins to find the best match in that color space. So in that case, we might care more about getting accurate colors than getting accurate total fluxes for the galaxies. And then you can also do galaxy modeling, where we're going to start making some assumptions about what the underlying surface brightness profiles of the galaxies are. When we use those assumptions, we can then convolve that model with the PSF and try to figure out what the best model is for varying PSFs across their bands. So in the next 20 minutes or so, we're going to take a deeper look into first PSF matching, and then galaxy modeling, specifically the SIRSIC modeling. Okay, so I said for the point source case, we know that they're both PSFs, so we can convolve one to the other and we should get a PSF out. We can do aperture photometry. In the case of extended sources, we're essentially doing a very similar thing, but let's consider a source with some unknown intrinsic surface brightness profile that we're going to call function S of X and Y. So here is our intrinsic galaxy surface brightness profile. We don't know what it is. We're not going to assume a form for it. We just know that it should be some function of position. Now, let's observe what the source looks like in two images with different PSFs. So we're going to have our PSF, which is a function of position f of xy, and then our second PSF, which is a function of position g of xy. And again, we don't necessarily care so much about what the specific functional forms of these PSFs are. We just want to know what they are. If we observe our intrinsic galaxy surface brightness profile S of xy through an image or through a detector setup that has a known PSF, the way that you can describe this mathematically is the convolution of your intrinsic surface brightness profile and your PSF. So what that looks like mathematically is down here. So let's call this S of f xy. So this is the source observed in this setup. And this is the integral. So this is the convolution integral, which means that for every point x prime y prime in our surface brightness profile, we're going to look at how the PSF looks like at a distance away from x prime. And we're gonna integrate all over x prime and y prime. And then this can also just be written as a convolution. So what this is doing is you're taking your surface brightness profile and you're spreading out the light at every point based on your PSF function. So you're going from something that looks like this to something that looks kind of, that looks wider. So you're spreading out the light because now you don't have an infinitely small PSF, you have a PSF of some known and finite width. This means that the apparent morphology of a source, so its size and sometimes also its shape, is linked to the PSF. So what you see and the kind of morphology that you see in these extended sources is also a function of the point spread function. Of course, it's a function of the intrinsic surface brightness profile, or at least we would hope that it would be. But it also changes as a function of your instrument detector coad characteristics. So same as in the point source case, we would like to measure some physical colors. We don't want to measure the difference between our PSF, whatever we do photometry. So one way to account for this is to PSF match all of our images to the worst PSF. And when I say worst, I mean the widest. So it's essentially the PSF that spreads the light out the most. And the way that we can do this is by computing the matching kernel. The matching kernel is the function k that maps f to g. Let's say that f is our better seeing PSF, g is our worst seeing PSF, such that you get out the worst seeing PSF if you convolve the better seeing PSF with your kernel k that maps f to g. So we want to essentially figure out the function that if we convolve it with the better seeing PSF, you get out the worst seeing PSF. The reason why we want to do that is because then we can just take this matching kernel and apply it to the full galaxy or the full image that has all of these extended sources in it, and essentially get an image in our better seeing band that has the same properties, has the same PSF as our worst seeing band. This will allow us to do aperture photometry in the same way as if they had exactly the same imaging properties. So that's essentially what I just said. The function that when convolved with the better seeing PSF produces the worst seeing PSF. So that's great. How do we actually do this in practice? One way to do this that's theoretically very, very nice, but often very noisy in practice, is to note that convolution, the convolution of two functions is the product of their Fourier transforms. So what I mean by that is, if you take the Fourier transform of the convolution between f and g, you will get the product of the Fourier transform of f and the Fourier transform of g. So if you have very, very nicely defined or even analytic PSFs, this can be an awesome way to figure out your matching kernel directly. In practice, when you have a PSF that you've measured empirically with some amount of noise, this method can blow up really quickly, because essentially when you Fourier transform and multiply them, you're really going to amplitude any kind of high frequency noise that you have in the PSF. So in practice, we often use some sort of filter or some sort of window to damp down high frequency noise in creating the matching kernel. In the problem set at the very end, I will ask you to do a matching kernel from the Fourier transform, but I'm specifically going to give you a form for the PSF that has a nice analytic solution, so you don't have to worry about noise. But in general, this is the way that we try to do this PSF matching. We try to identify the matching kernel, apply it to the better seen image. Then you get two images that have the same quality, same imaging properties as the worst seen. Okay. PSF matching is great because it allows us to do matched aperture photometry without making assumptions about the intrinsic source profile, S of X, Y. So that means that once we have these two PSF matched images, or really these n PSF matched images, you can have as many as you want. You can do aperture photometry directly and measure physical colors instead of the difference between the PSFs, which is awesome, but it also has drawbacks. So I think one clear drawback is that we're convolving to the worst seeing. And that means that we're throwing some information away from the higher quality data. And in general, we would like to use all of the information that we have, right? We've spent a lot of work over a lot of time to get these pixels, so we don't want to necessarily start throwing away information from our best data. So now let's explore what assuming a flexible function for the source profile, the intrinsic source profile S of xy, can do for extended source photometry. Okay, so let's go back to our convolution. So we said that the image that you see is going to be the convolution between the intrinsic surface brightness profile and the PSF. If we make assumptions about the shape of our intrinsic surface brightness profile, let's now call this S of xy given some parameters phi. For some profile parameters phi, we can predict what that convolution should be. So this is the convolution between our intrinsic profile and our PSF for our choice of parameters phi, and then we can compare that to the images directly. So in this case, we can use all of the information that we have in our better imaging quality data, because what we're going to do is vary phi and ask what we should see in each band, rather than convolve everything to the worst C. So, like I said, this allows us to account for differences in the PSF without convolving to the worst scene by predicting, let's say, the convolution between S and F, our better PSF, given some parameters phi, and S of G of X and Y, given those same parameters phi. So now we're not convolving to the worst scene, we're taking a base model and asking what that model should see, given the imaging quality in each band, and comparing that to the actual image that we see. Yeah, Vivek.
Say we're making assumptions about the shape. Which kind of shape? Is it like some type of elliptical?
Yeah, so there's a lot of there's a huge zoo of different profiles and different ways that people parameterize what the intrinsic profile S of xy should be. You can get, I would almost say, arbitrarily complex. I don't know if that's a mathematically true statement, but you can create very complex models to try to describe this unknown function S of xy. Yeah.
So are your model parameters the same for every band, and you're just trying to sort of optimize that, or can your shape that you get from this process vary across?
That's such an awesome question. So in the example that we're going to walk through, we're going to assume everything's monochromatic, so it doesn't change with band. But in general, one thing that we would like to do is have a model that changes with bandpass, and that is something that you can do. So the reason why we would like to maybe have a model whose morphology changes with band is that galaxies aren't just one color. If you have a highly resolved galaxy, you're going to see a lot of substructure. And one way we can learn about that substructure is by the relative colors between them. How much light is coming from one part of the galaxy in one band versus another. And so you might want a model that can account for that. So we're not going to talk about that today, but that's certainly something that you can do with this approach. Okay. So like I said, there's a huge zoo of ways you can do this galaxy modeling. Today, we're going to talk about one of the simpler cases, which is called the Sursic profile. The Sursic profile is used very widely today, but I'm going to use it as our example because it has a lot of nice analytic properties. But just to note that this is just setting up the framework for how you do galaxy modeling. You're not legally bound to only use Sursics for the rest of your career. Okay. Let's walk through first what the Sursic profile is. It's a very commonly used profile for smooth galaxy fitting. Its advantages: has a parametric form that can be easily convolved with the PSF. So that's very important if we want to do this kind of forward modeling technique, right? We want to be able to convolve our intrinsic profile S of xy with the PSF. It also has easily interpretable parameters, which I'll explain in a second to make this equation hopefully feel less full of parentheses. And the flexibility allows for fits to a broad variety of galaxies. So before I keep going, let's just talk a little bit about what the Sursig profile means mathematically. So first, I can look at this inner component here. So I have a surface brightness profile that varies with position. And I see that the position only really varies as a function of R. So when I say R here, I mean that R squared is equal to X minus the central position of X squared plus Y minus the central position of Y squared divided by the square of 1 minus the ellipticity. So just to remind you, 1 minus the ellipticity should be the ratio between the semi-minor and the semi-major axis. So that describes how much of a circle or how flattened the profile is. I should note that here I'm dropping some rotation terms just to make the math clearer. But essentially, if you wanted to have a rotated Sursig, you would apply the rotation matrix here in the R squared term. Okay, so we have a surface brightness profile that only depends radially on this elliptical radius. And we see that R appears as a ratio with this R effective term here. And then it goes to 1 over n minus 1. But let's just think a little bit about what happens when R is equal to this effective radius. So when we define this effective radius, hopefully it has some physical meaning for the model. Let's take R equals R effective. So this term becomes 1, which means this whole blue term becomes 0, which means this exponentiated term becomes 1, which means that the surface brightness profile I of xy is just equal to IE. What that means is that IE is defined as the surface brightness at the effective radius. And I should note that the effective radius is defined as the radius that contains half the light of the profile. That's not as easy to read off from the equation, so I'm just going to tell you, or just assert that the effective radius is defined as the radius that contains half the light or half the total light of the model. So there's also this n term that appears twice in the model, one as 1 over n, and then once in this constant bn. So bn is defined such that the gamma function of 2n is equal to twice the incomplete gamma function of 2n and bn. That's not a very interpretable statement. So what I'm going to do instead is show you what happens when we change what we call the Sursig index n. So the Sursig index n sets the profile concentration. Here I'm showing radius, oh, we got cut off. Radius versus surface brightness for n equals 1 down to n equals 4. So n equals 4 is in blue, n equals 1 is in red. The Sursig index n sets the profile concentration, and higher n means more concentrated, okay? So this is a parameter that sets the slope or sets the shape of the profile. So what we can see now is that we have 3 important parameters here that describe different physical components of the model. Now we have IE, which sets the overall flux of the model. If you increase IE, then your model gets brighter, it gets higher luminosity, higher surface brightness. You have this n term, which sets the shape of the model. If you increase n, the profile gets more concentrated. If you decrease n, it gets less concentrated. And then you have this R effective or effective radius term that sets the size of the model. So if you decrease the effective radius, it gets smaller. If you increase it, it gets larger. So you have this 3-parameter model where our parameters have a direct mapping to our total flux, to the shape of the profile, and to the size of the profile. This flexibility means that it's really, especially in the kind of small galaxy regime, where when I say small, I mean small in the sky, not necessarily physically small. When you get into the small galaxy regime, it does a really good job of matching a wide variety of profiles. So on the left here, I'm showing a cutout from the legacy survey, and on the right, this is actually a Sursig seed model that I used, or that I created using the same algorithm that I'm going to walk you through in the problem set. So you can see that it does a pretty good job of replicating the ranges of sizes and morphologies in these objects. One note that I didn't notice until just now is that we do have a under deblending problem here. So here, this is probably two objects. The model thinks that it's one, so it ends up as this slender galaxy. So deblending and fragmentation is always a tricky challenge. Okay, so I want to wrap up with a reminder that galaxies are complicated. So we've walked through PSF matching to get physically comparable or physically meaningful colors. We walked through using a Source model to model the galaxy light profile. But galaxies in and of themselves, as you get to higher resolutions, they depart more and more from our kind of simple Source models, which is great because it means that we're learning a lot of new information about these galaxies. We want to be able to see all of this substructure because it tells us something new about these different galaxies. But it also means that we need more complicated or more complex modeling approaches or more complex photometric methods to really get accurate and precise extended source photometry for these systems. And again, this is something that's only becoming harder in that our surveys are only becoming deeper, which makes deblending and fragmentation more of an issue. They're only becoming higher resolution, which means that we can see more of the substructure, which means that we need more complicated models. And so in this lecture, I'm trying to give you some of the tools for your toolbox, but probably in your research, you're going to think about trying to add tools to not just your own toolbox, but to our collective toolbox of ways that we can do this complicated problem of extended source photometry. So just to wrap up, simple parametric models are a great tool in the toolbox. I use Source models all of the time, but different science cases can use or need different approaches. So I'm going to flag just a couple up here. I'm happy to talk about these more, but these are a little bit more in the weeds. But things that we can extend, so we can think about more complicated or flexible galaxy modeling. So instead of assuming this very strict parametric form where I have 3 parameters, and those 3 parameters need to describe everything about the galaxy, I can try to relax some of those assumptions and make more complicated galaxy models to try to get closer to reproducing something like this. We can also do non-parametric detection and source photometry. So another thing that we haven't really talked about is not everything in the, not every extended source that we would like to learn something about is this nice galaxy surface brightness profile where it's brightest in the center and it drops off smoothly and radially. One thing that you might be interested in is diffuse light from comets. Another thing that you might be interested in is when 2 galaxies merge and they throw off these large tidal streams. Those don't look anything like a Source profile, but we'd still like to be able to measure photometry for them. So there's also techniques for non-parametric detection and source photometry that don't make assumptions about the underlying morphology of the system. And then also multi-scale detection methods. So another thing we might like to do is say, okay, we have this whole galaxy and we'd like to not just detect the boundaries of what is and isn't the galaxy like this, but maybe we do want to segment out some of this substructure while maintaining the knowledge that it is part of this wider galaxy. That's where multi-scale detection methods come in, like wavelet decomposition. But these are all tools that you can add to your toolbox, hopefully on top of this framework of our understanding of parametric and non-parametric ways that we can do extended source photometry. And so I'm going to give you hopefully a 10-minute break. I think we have time for that before we jump into the problem set, where we're going to think about applying both Source modeling and a little bit of multi-band photometry with PSF matching. So thank you, and I'll see you in 10 minutes if we have enough time for that. Oh, okay.
Yeah.
Okay, perfect.
Probably 5 questions so we can be in the top of the hour. As always on breaks, make sure that some portion of it, not